Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we're going to look at the qualitative analysis of ionic and molecular solutions. So I'm sure the first question is, what do you mean by qualitative analysis? And I'm actually going to give you the definition of the opposite of qualitative analysis, because I think that helps explain it a little bit better. So the opposite of qualitative analysis is quantitative analysis. A quantitative analysis would use number values, quantities. Qualitative doesn't use numbers. It uses usually visual things or simple tests. So it could be pH tests or a solution color, the color of a flame that's produced, or a precipitate that you can see. Those are qualitative things that you can visually see when you're working with solutions, or sometimes what you would visually see on, say, a multimeter when you're doing a conductivity test. So quantitative is with numbers, and qualitative is without numbers. So we're going to look at these 5 things, which I kind of just mentioned: conductivity tests, pH tests, solution color, flame tests, and selective precipitation. Selective precipitation is going to take it the most amount of time, but we're going to work through all of these kind of one at a time. I like to start with molecular solutions in terms of their qualitative analysis because there's a lot less to talk about here. So first of all, the biggest way that you can figure out whether you have a molecular solution or not is based on its conductivity test. Okay, and so a conductivity test measures electrical flow and charge. The biggest thing about molecular solutions is that they do not conduct electricity. Because there are no ions in solution. And the reason there's no ions in solution is it's a non-electrolyte. So a non-electrolyte has no ions in solution. So out of the 4 solutions that we're kind of covering in the solutions unit, which is molecular solutions, ionic solutions, acidic solutions, basic solutions, the only one that does not conduct electricity is molecular solutions. So if I was told I've got 4 solutions, and we've run a number of tests on them, and this one of the solutions doesn't conduct electricity, I can immediately say that that solution must be molecular because the other types of solutions that did conduct have ions and therefore are not molecular. Now, in terms of other tests with moleculars, we could do pH tests, but there are acidic, basic, and neutral moleculars. Remember, at this point, we're just talking about neutral stuff. So the neutral moleculars that you should know are things like alcohols, which would be CH3OH is methanol, C2H5OH is ethanol, sugars, which would include glucose, C6H12O6, or C12H22O11, and then also just pure water. That would be neutral as well. Now, other types of tests that are possible to do are things like solution colors. Now, all of these ones that I've mentioned here, which are kind of the ones we need to know at this point, are clear and colorless. So they don't have a color and they aren't opaque. You can actually look through them. So I use CC to represent clear and colorless. Most molecular solutions do not have a color. Not that we're dealing with it at this point yet. Going forward, the only 2 that really you come across at this level of chemistry that do have a color would be I2 in solution and Br2 in solution. And they're generally, depending on how concentrated they are in the solution, They're either kind of a yellowish brown or a reddish brown color. Some of you may have had iodine solution put on you. So iodine in solution can be used as a disinfectant before you get, say, an incision for a surgery, or if you have a really big needle. So for instance, when my wife had an epidural, when she was giving birth, they swabbed her entire back with iodine, and it stains your skin this reddy brown color, and you got to wait for it to come off. You can't scrub it out. Or I had surgery on my pinky finger to have a tendon fixed, and before they made the incision on my finger, they swabbed my hand with iodine, and then they made the incision, and then they started to do the surgery. Or a lot of you may have just gone to get needles done before, and sometimes before they give you a needle, they'll swab your skin and it's a reddish brown color. That's iodine, okay? I'm not asking you to memorize these. I'm just saying that out of moleculars, those are the two that you may come across in terms of solution color. It would be something that you would have to memorize, but I don't think it's important at this time right now. Thought I would just mention it. Molecular solutions have no flame colors. Most solutions that have flame colors, when you put it into a flame, a hot flame, have to have a group 1, group 2 metal, or there's a few transition metals that will produce flame colors. And because they're molecular, they do not have a metal ion in it or a metal in it, and so it's not going to produce any type of flame color. And we cannot selectively precipitate molecular solutions because we need ions in order to selectively precipitate. So no selective precipitation, which we will deal with last, because there again no ions present, and there's no flame colors because there is no metals present in these molecular compounds. So to summarize, realistically, if I want to identify an unknown solution as a molecular, I'm focusing almost 100% solely on its conductivity test. The solution will not conduct electricity. So what that would look like is if I had a multimeter, which has a little digital readout, okay, or it could even have a needle, okay, so it would have a needle like this, and there'd be a bunch of readings on it, and then you would stick the two electrodes, which would be just kind of like wires with a metal point on it. One will be red, one will be black. You would stick these into the solution. I'm going to make a solution here. Okay. And this will read basically 0 or very close to 0, and the needle won't move. It'll be barely deflected. It's very hard to remove all ions from solutions, but essentially the needle will not deflect or move. The voltage current being produced will be essentially 0 or very close to 0. That's how you figure out whether you have a molecular solution. Now, the majority of our time is going to be spent on ionics because they do a lot of these different things. So for instance, all ionic solutions, they all conduct electricity. Under the assumption that we're dealing with things that are soluble. We don't have a solution if the thing doesn't dissolve, but all ionics that do dissolve in solution, they all conduct electricity. The more ions you have, the more conductive it is. So the higher the concentration of ions in solutions, the more that needle is going to deflect, or the higher the readout for the conductivity. So more ions, more conductive. Again, I'm just going to use sodium chloride as an example here. When I put this in water, it becomes sodium ions, which are charged, and chloride ions, which are charged. And so I'm going to get a charge. I'm going to get a flow of charge. So again, if I was to look at, say, a traditional multimeter, it would have, a needle here. When I put this in a dial and I move the dial to a certain setting for a certain reading, when I put this in solution, the needle is going to move across, or if it's a digital readout, I'm going to see some kind of voltage or some kind of current depending on what setting I'm using. The next type of test I could do is a pH test. Now, I'm going to give some broad general things here in terms of pH because we haven't discussed acids and bases yet. But just keep in mind that a neutral ionic compound will contain a group 1 or 2 metal cation. So for example, it could be potassium, lithium, sodium, calcium, magnesium, zinc, something like that. And then it's also going to have one of 5 anions, which are neutral. These are the conjugate bases of 5 of the 6 strong acids. So chloride, bromide, iodide, nitrate, perchlorate, in combination with these. Now, this is a general rule. There is always some kind of exception somewhere, but as a general rule, we are pretty sure that these are neutral ionic solutions. I don't want to get into what you would have with other ions in too much more detail, but generally most anions will act as a base, and we will deal with that when I start talking about bases. The other thing that I'm just going to mention briefly is, why does it have to be group 1 or group 2? The answer is there are other cations which are neutral, but they are very specific. Like, you have to know exactly which ones. So for instance, some of the transition metal ions, some of them are acidic. The most commonly known acidic cation would be something like iron 3+ is very acidic. The reason why it's acidic is beyond the scope of our course. It takes a little bit to explain, but this is actually a major problem when you are mining iron ore, and then there is a slurry water that comes off that contains iron 3. The pHs can be extremely low. They could be 1, 2, 0. And often this will leach into nearby lakes or ponds or rivers, killing the life in it. So it's very acidic. Copper ions as well can be acidic. So some transition metals can be acidic in solution, some aren't. This is really beyond the scope of what our course needs us to understand, but I thought I'd mention it kind of to preempt questions of why is it just group 1 or group 2 ions. Okay, so we're just going to worry about neutral ionics for now. I've mentioned this before, I've mentioned it again now. This is what we're going with in terms of what is a neutral ionic compound. The next way I can test a solution to see what kind of ions are present are solution colors. Now, most ionic solutions are clear and colorless. Now, the reason why I have clear is you can have opaque, so it's hard to see through, or clear, you can completely see through. So water would be clear and it would be colorless. Okay, if I had Kool-Aid, grape Kool-Aid, depending on how much grape Kool-Aid I put in, it could be clear and purple, or it can be opaque and purple. So a clear and purple Kool-Aid drink, if I hold the glass up in front of my face, I could see through the Kool-Aid to the other side. If it was opaque and purple, I'd hold the glass up to my face and I couldn't see through it. It would have a higher concentration of purple color. Okay, so most solutions are clear and colorless. Some solutions have color. And about 90% of the ones that do have color, the color comes from the cation. And about 10% of the time, the color comes from the anion. And you can look these up. This is not something you need to have memorized. So let's go to the data book and have a look at where these are. So here is a table of common aqueous ions that have a solution color. So some of them are anions like chromate, CrO4 2-, dichromate, Cr2O7 2-, or permanganate, MnO4-, but the majority of them are actually transition metal cations. So chromium 3 to cobalt, copper, copper, iron, manganese, nickel 2, those are all transition metal ions, and they will all produce a color in solution. Now, what you'll notice is they have two different colors, like yellow and pale yellow, blue-green or green, dark blue or pale blue. And this is just based around the concentration. And so I'm going to use my purple Kool-Aid example as an example. If I put very little purple Kool-Aid crystals in water, it's this really pale purple because I don't have much in there. But if I put lots of purple Kool-Aid crystals in water, then I get this really deep, nice purple color. And so that's why you get these two different colors. For instance, if you look at the bottom, permanganate is a very, very deep, beautiful purple color when it's at about 0.1 moles per liter. But anything below that, you get kind of a lighter color of purple, purple pink. This is opaque, you can't see through it. This is clear purple, you can see through it. Now, for our questions, or the purpose of our questioning, we're really going to be using just this one here. Most solutions that are made are going to be in the 1 to 0.5, 0.1 moles per liter, and realistically, all of those are going to be in this region. This is much less concentrated, so anything in here would be a solution color. So for instance, ones we come across a lot, copper 2 being blue, permanganate being deep purple, iron being an orange yellow, but these are all different types of solutions that have colors. Anything that does not appear on here, we assume to be clear and colorless. So for instance, sodium is not on here, so this sodium would be a clear and colorless solution. We know this because salt water is clear and colorless and it contains sodium ions. Now the next type of test we're going to look at is a flame test. Now this table is for solutions, but this table is for flame colors. Now you can do flame color tests with solids. You can do it with, say, lithium chloride solid. I could put a little bit of lithium chloride solid on a metal wire. I could put it into a Bunsen burner flame and it will produce a beautiful red color. Or my favorite one is potassium. I could put some potassium chloride solid on a metal wire. I could put that in a Bunsen burner flame and it goes this beautiful violet lilac color, it's a really nice color. So two other ways of doing a flame test would be the following. Now both of them would require having a flame source. So I'm going to say that this is a Bunsen burner, and you would have to have that Bunsen burner on very hot setting. So it would actually have a blue flame like a torch. in order to be hot enough to cause a flame color to happen. Now, traditionally, what I've done in the past is I'd have a beaker and it would be filled with a solution. So I'm going to call this a copper 2+ solution. And I would soak some coffee stir sticks, the wooden coffee stir sticks in them. So I'd soak that. And then the stir stick itself would start to turn blue because the copper 2 ions are blue. So this would start to turn blue and it would be very moist. And then what I would do is I would take that and I would put it into the flame. So then I go and I put my soaked stick in that flame. And then what you would have is this beautiful, bigger green flame. And it would be blue as well. This bluish green flame would come off of it. And it looks really, really nice. So that's one way of doing it. The other way of doing it is you can take a spray bottle, like a Windex spray bottle. I'm not an artiste here. Okay, and inside of the Windex spray bottle, you would put the solution of copper 2 ions in it, and you'd spritz the flame, and the same thing would happen. You get this beautiful flame color coming off. But that's a different way of doing a flame test that works really, really well. The last type of qualitative analysis we're going to look at is called selective precipitation. Now, you should remember that precipitation is when you have a solution and you add another solution to it, it will produce a solid in solution. Now, selectively precipitating something means that you would add a specific solution to specifically remove an ion that is in another solution. Now, you can do this to remove one solution, or you can do this to remove multiple ions in solution, one at a time. So I have a solubility table here. And I'm just going to do some simple precipitate questions first, and then we'll look at a more complex selective precipitation question, and I'll describe to you how it would be done in the lab. So let's say you are given a solution which contains copper 1 nitrate and silver nitrate. Let's look at what ions you could add to this solution that would actually precipitate out both copper 1 and silver ions. Now, this wouldn't be classified as selective precipitation because I'm not removing just one of the ions. I'm actually removing both. So we're just trying to find different ions that would actually remove both copper 1 and silver. Now, I'm actually going to start over on the right-hand side here. So for instance, hydroxide is only soluble with group 1 ions and NH4+. Copper 1 is a transition metal, and so is silver. They would actually fall underneath most. So I know that I could use hydroxide ions to remove both. Just moving across, iodate and oxalate ion are here. They are soluble with group 1 ions, which copper 1 and silver are not, and with NH4+, cobalt 2, and iron 3, of which we don't have. So that means that they would fall underneath most as well. So iodate could be used, and so could oxalate. And the same thing is true over here. Silver and copper 1 are not here. They would fall under most. So there is actually lots and lots of ions which would precipitate both of these things at once. So I got carbonate, phosphate, sulfite. As I move across, we're getting into more detailed stuff. So sulfate is soluble with most, but it is insoluble with calcium, strontium, barium, silver. It is insoluble with silver, but it actually is soluble with copper 1. Now that would actually bring us to our next question, so I'm going to kind of do them in tandem. It says, what ions could you add to just precipitate out the silver? Sulfate could be used just to precipitate out the silver because copper 1 is not part of this list. Copper 1 actually falls underneath most. So sulfate, SO4 2 minus, could be used to only precipitate out the silver. Now let's move across. Chloride, bromide, and iodide are soluble with most things, but they are insoluble with copper 1, silver, mercury, lead 2. So actually, those things would precipitate out both. So I could add this to my list. Chloride, bromide, iodide, these are all insoluble with silver and with copper 1. Moving over, fluoride is soluble with most except for these. And silver and copper 1 are not part of that, so they would fall underneath most, so I can't add that to my list. And then I move on. Group 1 ions and all of these are soluble with almost everything. However, they are insoluble with... acetate is insoluble with silver. That is an exception. So I'm going to add that to my second question. What ions could you add to just precipitate out the silver? I could add CH3, COO-, which is insoluble with silver. And there we go. Those are all the ions we could use to precipitate out both copper 1 and silver. But there's only 2 that could only precipitate out silver. So that's just a general idea how to use the solubility table and to kind of come up with these ideas. What we're about to do is a proper selective precipitate question. So this one says, plan out how you would precipitate out the following 3 ions. And the key here is 1 at a time. We only want to remove 1 ion at a time. So I'm going to draw what it would look like or how I would do it as we go. Now there is multiple correct answers. The way that I do it now is not the only possible answer. So maybe what we'll do is we'll do this twice. We'll do it 2 different ways. But this is what I mean. What I would start with is I have a solution. I've been told that in this solution I have Pb2+ ions. I have silver ions, and I have copper 1+ ions. And what I want to do is add a solution to it to remove one of them first. Then I want to add another solution to remove another one. And then I want to add a different solution to remove the last one. Again, there's multiple ways of doing this, but we are going to go back to our solubility table and look at how we can do this. So I'm going up to the top. What I'm going to do is I'm going to highlight silver, copper 1, and lead 2, wherever I can find them here, because I don't want to look around over and over and over again. Here's lead 2, and here's silver. And a lot of the time, they will also be falling underneath most here, here, and here. So realistically, this most here would include the silver, it would include the copper, it would include the lead too, all the way across these. So what that tells me is I can't use any of these ions to selectively precipitate out these ions 1 at a time, because if I added any of these ions up here, they would precipitate all 3 out all at the exact same time, and that's not what I want to do. All right, I'm going to keep moving this direction and we'll talk our way through this. So let's say I added a solution that had sodium sulfate in it to my beaker. What would happen is silver and lead would both precipitate out at the exact same time. That is going to be no good for me because I want to selectively precipitate out only one of them, and it's taking out both. Let's move over. I can't start with sulfate. Let's move over. If I had, say, sodium chloride or sodium bromide or sodium iodide solution, and the only reason I keep saying sodium is because it's 100% soluble with all these things. If I added these solutions to my beaker, it would precipitate all three out at the exact same time. So I can't use these ions to selectively precipitate out one of the ions. Now, as I move across, I actually have two ways I could start this off. If I had a solution that had fluoride in it and I added it to my beaker, it would only take out lead, which means I would have selectively precipitated out the lead, one of those things, and the silver and copper one would still be in solution. Or I could add, say, a solution of sodium acetate, and it would selectively precipitate out only the silver. So I actually have two starting points, and I think what I'm going to do is I'm going to start by removing the silver by adding acetate, and when we do it a second time, I'll start by adding a fluoride ion to remove the lead too, in a second way of doing it. So let's go back down to the bottom here. So what I would do is I would make a beaker containing a solution of sodium. I guess I should make it a bit bigger. So I would add a solution which contained sodium acetate. Now the sodium is just there because I need a cation, but I'm really more interested in the acetate, and I would pour that into this solution, and what would happen is I would form solid silver acetate at the bottom of the beaker. So this would be silver acetate, solid, but the lead 2 would still be floating around there, and the copper 1 would still be floating around there. Okay. So I have selectively precipitated out my silver. Then I would have to remove this solid from the beaker. So I'd set up a filtration apparatus with filter paper. So I'd have a funnel, and inside of that I would have filter paper, and I'd put a beaker underneath it. Okay, and I would pour this solution in here, and it would drip through. It would drip through, and what I would be left with is lead 2 plus and copper plus there, and all of the silver acetate would get stuck in the filter paper. So I have removed the silver acetate. So that would be my first step. Okay, now I would have a beaker containing only lead 2 and copper 1. I got to find another solution to pour in here that will only remove one of them. So let's go back up to our table and we'll find something that has just one of them. I'm going to erase the silvers because this is gone now. It's gone. I don't care about it anymore. So I'm looking here. It looks like I got a few possibilities, and it does look like I'm going to remove the lead next. I could add something that has fluoride ion, or I could add something that has sulfate ion. And if I did that, it would remove the lead. It would remove the lead, and only copper 1 would be left behind. So I'm going to say, I'm going to pour in a solution of sodium sulfate. I'm going to pour this into here, and what would happen is now at the bottom of my beaker, I would have lead sulfate precipitate. So this would be PbSO4 solid, and then the copper 1 would be left behind. So now what I would want to do is I'd want to pour this again through filter paper. I'm just going to do this below. So I would pour this solution through filter paper, through a funnel, and I would collect the remaining amount. So now the lead sulfate solid is going to get stuck inside of that filter paper. I'd have a beaker underneath, and I would collect the remaining solution, which would contain copper 1 plus. Now, at this point, I'm just going to start back over here. At this point, I can add dozens and dozens of different ions into this solution to get rid of copper 1 because it is insoluble with so many different things. So I could, at this point, I could add, let's go to the top, I could add any of these. Are all insoluble with copper 1. I could add any of these. They're insoluble with copper 1. Copper 1 is here. Lead is already gone, so I don't care. So now I could add any of those 3 or any of those 6. So I've got 9 options there that I could use. I would probably add in something like, I would add in sodium chloride. I'd add that in. It would precipitate out. And then I could filter it a 3rd time. I think you guys are getting the gist. Okay. So that was my scenario. So the first thing I removed was silver by adding acetate ion, CH3COO-. The second thing I removed was Pb2+ by adding in sulfate ion. And of course, I just said it was with sodium because sodium is soluble with everything. And then 3, I removed the copper 1 by adding sodium chloride solution, or I can just say chloride ion. And really, I could have added hydroxide, iodate. There's tons and tons of different options. So I've ran out of room here. I'm just going to give you my second scenario. There's, again, multiple ways of doing it, just to make sure you guys are all on board. So I'm going to undo those. I'm going to re-highlight lead, silver, silver, lead, and then acetate. So here's just a theoretical number 2. What I could do is I could add sodium fluoride and remove the lead. So that would be gone. Then I could either add sulfate or acetate. Let's say sodium sulfate. That would remove the silver. That's now gone. And then I could add any of these 3 to remove copper, or any of those 6 to remove copper, and then I've selectively precipitated out the copper. So there's just a second scenario. I'm sure I could come up with 1 or 2 more. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.